Hello again, this is Foghorn with another installment of Flight School Academics for this, the 5th of December 2020, or 2950 if you are way off in the future. This presentation is part of an ongoing series of academics for the members of the Aurora Republic, the premier role-playing organization in Star Citizen. If you are new to the Aurora Republic or visiting for the first time, let me start by saying welcome. We're glad to have you with us and would love to hear more from you if you are interested in hearing more from us. We are a lawful good organization focused on roleplay exploration and social interactions and are currently active in recruiting on Spectrum and Discord. First, let's a couple of announcements from the org itself. First off, we have some new members. We got 2 new members this week, Callsign Reaper and EOD Medic. Welcome to the family. Love to have you there. In addition, everybody say congratulations to Callsign Reaper, who immediately went in and started flying around with us and got rid of his immigrant tag right off the bat. So he's a full citizen. So everybody pat him on the back and say welcome and congratulations on earning your Aurora Republic wings. Org announcements. Next week is the full org meeting at 2000 hours Eastern time on Saturday, 1 week from today. So maximum participation, maximum attendance. If you're not really playing Star Citizen right now, but you are checking in on the academics and stuff like that, and you hear this during the week, full org meetings, the quarterly full org meetings are absolutely paramount that you should probably catch to at least get the minimum amount of participation, knowledge, and know what's going on in your org. Second big thing, during the anniversary sale last week, the org picked up several more org-owned assets to increase our fleet. However, one of those is a capital ship, basically a Pioneer, and we are going to have a naming ceremony next week, Saturday, immediately following the full org meeting. The naming ceremony, for those who were not here the last time we did this, when we named our first capital ship, it is a raucous good time. It is a party. Master ceremonied by myself playing the sheriff, and we will, for the next week, we're going to have open suggestions. We'll be taking suggestions for names for the Pioneer as our third capital ship in the org fleet, org-owned capital ship. The first one being, of course, the CCE Independence, and then the CCE Robert C. Clemick was the second one, the Idris. And then the Pioneer we're going to name next Saturday. So the next week here, we'll have a Discord announcement that will tell you where to make your submissions of names for the Pioneer. You can make as many suggestions as you like. And then we have a system that involves basically reverse voting. It's a hell of a lot of fun that we will do next Saturday immediately after the full org meeting. So expect it'll be an hour or two of fun, sarcasm, hilarity, mocking each other, and voting what names you want to keep on the board and take off the board, and all of that sort of thing. We'll explain the rules to the party at party time, at the beginning of party time. So, anywho, don't miss that. It's a hell of a lot of fun. We had a great time last time, and last time we raised about $200 for the org coffers through various buffoonery and penalties and selling of what was the left of anybody's shame or self-worth. So it'll be a good time. It is, however, a private ceremony that is only for org members, just like the full org meeting. Unlike our academics, which we would make open to the public, the full org meeting and the naming ceremony will be private. It'll be done privately and streamed privately and should not be shared, because there should be embarrassment. There will be embarrassment. I guarantee you that I'm already embarrassed. So anyway, rules of engagement for tonight. We are streaming this video on Twitch. There is a broadcast delay. I'm monitoring the Twitch chat as best I can. But being only able to leap tall buildings with a short running start, then I often can miss things. I will answer questions I see there as soon as I see them, but you can also just unmute yourself in the academics channel and ask in real time. I'll stop and answer questions as we go if you ask them in real time. If you are monitoring, if you're both in the Twitch chat, the Discord chat, and listening along with the video on Twitch or the slides on Twitch, then you probably want to deafen one of those so you're not hearing me echo twice. This is a big block, what we're doing today, and it's actually a redo, if you will, a revisit to several different smaller pieces that as we've been consolidating and improving and streamlining our academics and our training syllabus, we are starting to get these things formed into actual cogent modules. So we're going to go over the basic aviation concepts module, which is the first one for the undergraduate pilot training syllabus. That will be coming soon to a torture chamber near you, and you will be subjected to if you decide to go this route into our combat aviation futures. So this probably is going to be a little bit long. I'm going to haul ass through it. I'm going to be talking fast. This is stuff that has been said before, unless you're sort of new to the org, for these basic aviation concepts and how they apply to Star Citizen. Okay? So, without further ado, and to our wonderful video curator and director of communications, Brat Farrar, you and I need to touch base later on this week, because this particular one is going to replace probably 7 or 8 of the other previous videos that are in our archive. So this is a consolidation of them. Okay, so faster and funnier. All right, so basic aviation concepts in Star Citizen. These spacecraft move in what's called 6 degrees of freedom movement. So along the 3 axes of the spacecraft, you can translate and you can rotate. I'm going to demonstrate this and show it to you with a demo in Arena Commander, plus some of the features of the Intelligent Flight Control System modes. So that's where we're going to go from here. All right, so the 6 degrees of freedom, like I said, you have 3 axes that are going through the spacecraft. The x-axis goes longitudinally, so forward and back through the front and back of the spacecraft. The y-axis goes laterally through left and right through the midsection of the spacecraft, and then of course the vertical axis is the z-axis, which goes down through the top and bottom. Okay, so that gives you 6 degrees of freedom because you can translate along each of those 3 axes, and you can also rotate around each of those 3 axes, which is where you get the 6 degrees of freedom. 3 translational degrees, 3 rotational degrees. Now, to translate along those axes, there is actual proper terminology that we're going to be using, and I'm going to be a little bit Nazi-ish about it because, 1, it's correct, and 2, I like it. For everybody who likes to call translating along the axis strafe, we're going to strafe forward, strafe back, strafe left, strafe up, strafe down. You're an idiot. Okay, I say this with authority that you are absolutely an idiot, because that is not strafe. Strafe is what happens with a machine gun. If a machine gunner in the Army is spraying bullets along a line, kind of getting them to ricochet off the hill, trying to keep people's heads down, that is strafe. An aircraft comes down with a machine gun, goes and throws bullets along a line down at targets on the ground, that is called strafe. When you translate in the three translational degrees of freedom, their terms are actually surge, sway, and heave, to use the proper aerodynamic terms in aeronautical engineering. So, and then of course the 3 rotational axes, roll, pitch, and yaw. Let me find my laser pointer. Okay, so along the x-axis, the red axis here, if you translate forward or back, that is called surge. You're going to surge forward or surge back. If you translate along the y-axis, this yellow one, then you are going to sway left or sway right. And if you translate along this blue axis, up and down, then you are heaving up or heaving down. The same thing if you, so along this axis that you surge, the x-axis, if you rotate around it, according to such as this green half circle arrow, if you rotate around that axis, that is called roll. If you rotate around the yellow left-right lateral axis, where your nose goes up or down, that is called pitch. And if you rotate around the vertical axis, the blue one, where your nose follows the orange half circle 3D arrow, then that is called yaw, where your nose swings left or right. That yaws left, yaws right. And I will actually use those terms throughout the rest of this presentation, and anytime that you're actually flying with me as your instructor pilot during any sort of an educational sortie, then you'll also hear me say, roll this, pitch that, yaw there, surge here, sway left, heave up, so that I need you to be familiar with those terms and not expecting me to say strafe. If I'm going to tell you to strafe something, that means I want you to open up the gun and make somebody's day suck. Okay, so I'm going to kick into the flight demo and demonstrate each of these very quickly. Let me get rid of the laser pointer. Okay, but I need you to pay special attention to this flight path marker. It has changed. The symbol for it has changed in, I think it was last patch. It's no longer that rounded square with a caret at the bottom. It's now these two opposing carets that either point towards each other if this vector is forward from your viewpoint, or they are away from each other if the vector is actually back out the back behind you. Okay. And I'm just going to quickly go through that and show you the IFCS modes as well. So let me Alt-Tab over here. So here we are in Arena Commander. I do have my track IR working, so I can look left and right and up and down, and that should help us demonstrate this thing. Okay, so here I am in the mighty Consolidated Outlands Mustang. In Arena Commander privately, or not private, but single player in free flight, and looking at an asteroid fairly up close and personal, just so that you can have a visual reference to see what is happening with the spacecraft, because a lot of times out in space it's hard to visually tell what's happening. So the first thing I'm going to show you, I'm actually going to point off over here a little bit, and I'm going to push, and I'm going to see, if you see over to the right above the where it says fuel, you will see that those two carets pointing towards each other. I'm surging forward with a little bit of a sway to the right, that to put that flight path marker outside of out of the gun cross, because you'll notice when it goes in front of the gun cross, it disappears, or almost disappears. It gets very dim. It shows up more brightly when it gets outside of that, so that you can see that this is what it looks like when you're going basically forward. The line from my eyeball through that on my video screen is the vector that this spacecraft is flying with. Now I'm going to stop and go backwards. I'm going to do the same thing. I'm going to put myself in a back and a left, strafe back and sway left. And now you'll see that those two carets are now opposing to each other, because I'm actually flying backwards. And you can see that by watching that asteroid go moving by. Okay, so now, all right, so the three rotational axes, which are what pretty much everybody is used to hearing already: pitch, roll, and yaw. So, of course, pitch, you're rolling around the y-axis, which is your lateral axis. This pitch is when the nose goes up and the nose goes down. Okay. Yaw is rotating around the vertical axis, and that's where the nose goes left and the nose goes right. So that is yaw. And then the x-axis, the longitudinal axis, goes straight forward and back out the front and back of the spacecraft. So if I rotate around those, then that is roll left, roll right. Those are the three rotational degrees of freedom. Now the three translational degrees of freedom. Obviously, I already showed you that I can surge forward, and I'll put it a little bit offset from center so that you can see the flight path marker. And I'm going to come to a stop, and you can see the asteroid getting bigger. I'm going to surge away from it. Again, I'm going to go slightly aside, so the you can see the flight path marker is now the two carets up, pointing away from each other. All right, and then I'm going to go to the right now. I'm just going to go straight right. So if I turn my head, there's my flight path marker. I'm swaying to the right. And now if I push opposite left, you can see that my flight path marker moves, and then it comes back around over here. Boop. As I start swaying left, there's my flight path marker saying I'm going out over there. And as you can see, the asteroid is moving appropriately. Okay, let me get back to a stop. All right. Okay, so the last one is if I heave up, you can see I go up, and the flight path marker is up there. I'm going a little slightly back too. There we go. And then if I heave down, I can look down here and see there's my flight path marker going down between my feet. And you can actually see my shadow on the asteroid over there. There you go. So that's the 6 degrees of degrees of freedom being demonstrated to you. Now, the Intelligent Flight Control System, IFCS, has a couple other modes that you can engage and disengage. The first one is coupled and decoupled flight. You'll see down in the lower left corner of my HUD, you will see gear, CPLD, and ESP. CPLD and ESP have dots next to them. CPLD stands for coupled. If all I do is simply drone forward, coupled means that my flight path marker, if all I'm doing is surging forward without putting any sort of other translational input in, when I turn my nose, the flight path marker the IFCS attempts to move the flight path marker back to wherever my nose is. That's what coupled means, is that you're controlling your flight path marker with your nose. Some people say, means it flies like an airplane. Now, that's true, that's the intention, and coupled actually means something in modern day space terms that CIG is taking a little bit of liberty with, which I take issue with, but I'll take that up with them. Is if you're, let me hit just cruise control mode here, so I'm not using my translation sticks at all. If you push hard enough, you can just pull your nose away from the flight path marker faster than the IFCS. And you can actually push it all the way around just as if you were decoupled. And you can see I can even just bury the stick and I can chase my flight path marker around instead of it staying underneath my nose. In my opinion, actually it's not my opinion because NASA and ESA and ICAO and the FAA agree with me, that is not what coupled flight means, that your IFCS should prevent you from being able to turn any faster than your thrusters would be able to move the flight path marker to keep it underneath it. That's, however, this is their video game, so they can do it however they want, even though I think it's bullshit, because it is. So, short story long, you can also decouple. So I'm going to hit my switch to decouple here. I believe it is Victor on the... and now what it means is that now, if all you do is rotate, as you can see, my flight path marker hasn't moved. I can push my nose wherever I want, and the jet is not going to attempt to change my flight path marker until I give it a translational input. So if I push forward, now that flight path marker starts, because I'm using my forward surging thrusters, my main thrusters, you see that it pushes the flight path marker back over towards the nose because I'm just pushing forward only to surge forward. Like, if I point the nose down, I'm not actually flying down. I'm flying that direction out the top of the spacecraft, even though I'm pointed that way. This is what decoupled can do for you. Now, the second I couple it back up, if I don't touch my inputs at all I do is couple. Now, because I'm not in cruise mode, the IFCS immediately fires whatever combination of thrusters it needs to bring me to a stop along that vector that I had. If I have cruise control engaged, which is done with the Charlie button, then whatever you have on your speed limiter set over here on the left, which you can control that with your mouse wheel, if you're a keyboard and mouse flyer. When you hit Charlie, then the IFCS says, okay, you want a constant speed of whatever that line is set to. And as you can see, as I turn around, you see that the speed comes off as it moves the flight path marker, because it's using the combination of the thrusters in all different directions that it needs to move that flight path marker. But then a second it gets back to where I'm pointed, then boom, it immediately goes back to 193, which is what the SEM is for this particular space vehicle. All right, so that's IFCS that's coupled, decoupled, and cruise control. The third one I'm last going to show you is auto land. So over here in Arena Commander, you have these practice landing pads if you feel that you need some landing practice, and some of you do. Okay, so if you come over top, and I think these have auto land capability, but they might not. Make sure that your gear is down. So when you hit November to move your gear, you'll see that the gear light will blink while the gear is in transit, and then the little dot will come up second when the gear is down. And I can go into third person view rotate my view down and see, yep, my gear's down. Okay, great. Come back into first person view. Okay, so I'm going to surge forward until I get over top of the landing pad. I did not actually check this prior to make sure that this works in Arena Commander. It might not. And then where normally, see, I've got, I don't know, what, 10, 20 feet hovering over top of the pad. If I hold N down, it should kick into auto land mode, and it brings me down and lands me all by it. Well, not all by itself. The autopilot does it. So if you're really bad at landing, this is your, as we say, all fucked up recovery. I would suggest you always attempt to land manually. Not because there's any problem with landing as autopilot, auto land, but I would, as a skill builder, always try to land by hand. Because if you got it set up right and you know how to surge, sway, heave, pitch, roll, and yaw, doing this right here should be a no-brainer. You don't need the computer to do that. You can do that yourself. Huh, interesting. Why are you rolling? Huh. Okay. Gravity on the pads might be weird. All right, so there you go. There's a flight demo on the 6 degrees of freedom and the 3 IFCS modes I wanted to show you. Boop. Okay. All right. Don't bring me down. Ooh, ooh, ooh. Okay, so the next section we're going to talk about is celestial navigation. Now that we know how to properly discuss moving our jets around in space, now we're going to need to know how to navigate around in space. And there's actually, this is going to sound a little complicated at the beginning, but it actually all works off of one system. CellNav works all off of one system, and it's basically something in physics known as a spherical coordinate system, and mathematics known as a spherical coordinate system. The coordinates that you're used to hearing, X, Y, and Z, is called Cartesian coordinates. They are not good for anything outside of mathematics, really. Cartesian coordinate systems are basically not good for a whole lot out in the engineering, real world, physics, sciences. They just make math really easy when you're trying to teach children mathematics and the concept of a three-dimensional space. So in astronomy, in the aerospace industry, in pretty much all engineering disciplines, pretty much all coordinate systems are done in spherical coordinate systems. So what makes up a spherical coordinate system? These are the following components. It starts off with an origin point, so a center of something. That's 0 point. That's the point where everything starts and is measured from. You have a fundamental plane, which defines what is 0 degrees of latitude, and everything that is in that plane is 0 degrees of latitude. And yes, Victor Vale, this is exactly the Star Trek X. Yeah, exactly. Turn left, 354 Mark 20. The 354 is the longitude or degrees off the nose heading, and then the Mark 20 is 20 degrees up. That's what the Mark 20 point is, and I'll show you more of that in a minute. Primary direction. Okay, so if you got your fundamental plane, the third part of a spherical coordinate system is a primary direction. So you have to have something that defines this is 0 degrees longitude. So in a spherical coordinate system, your origin, what you choose as the center point, is important. So when you're talking about navigation, that center point should probably be something, that origin point should be something that is naturally occurring and of some sort of an importance that you'll always be able to find or see or know where it's at. The fundamental plane, same thing. Primary direction, same thing. When you're using a spherical coordinate system to turn it into some sort of a navigational system, then those three things that you choose are important, and they should be things that natural geography out there that those things that you point should be some sort of natural geography that is important somehow, relevant somehow, significant is the word I'm looking for. Okay. Of course, once you got those three, then everything else falls into place. 90 degrees of latitude up and down from off of that fundamental plane is your poles. And then the system will have a circular convention of either being a left-hand circular or right-hand circular. And so if you remember back from science class, remember right-hand rule, then right or left hand means it's either a right-hand rule or a left-hand rule. And the vast majority of spherical coordinate systems in existence in the universe are right-hand rule. There is a left-hand. There's a couple that are left-handed, left-hand rule oriented, but the vast majority are right-handed. Which therefore, everything, or your coordinate system is given in a longitude, latitude, and a range. So as you can see out there, we have an object, that star, up on our little diagram there, that is up in three-dimensional space, away from our origin, up off of the away from the line, the 0 degree line of longitude, the primary direction, and somewhere up out of the primary plane. So how would we describe that? How would we find that longitude, latitude, and range? You'd first, starting from the primary direction, the 0 degrees of longitude, it would, we're going to assume a right-hand convention, circular convention system. So from that, we would measure counterclockwise around to the direct within the fundamental plane to directly underneath that object that we're trying to measure to. That would give us our x degrees of longitude. We would then measure the angle from the fundamental plane up into an imaginary line going from the origin out to that object. That would give us our y degrees of latitude, and then you would measure along that imaginary line out to the location. That would give you your range. So those are your still a three coordinate system, just like Cartesian was x, y, and z, but in spherical you're going to get lat, long, and range, or long, lat, and range. And it's actually done longitude first as the convention. So x, y, and r. So lat, long, and range. Okay, so the actual celestial coordinate systems that are in use today in science and astronomy and astronavigation and astrophysics, there are several. There are 5, basically. They are all spherical coordinate systems. So that's why I taught you that first, is how a spherical coordinate system works. So the difference between them is basically their frames of reference. So the first one is the horizontal coordinate system, which you are actually familiar with already, because this is how you navigate around on the Earth's surface. When you pull out a compass and you look down at it and you go, okay, I need to head bearing 280 for 15 miles, and that'll get me to my destination. You're using the horizontal coordinate system. And I will show you a table here on the next slide that'll show all 5 of them and what those components, where they are for that system. Next one is the equatorial coordinate system, which is what pretty much all Earth-bound astronomy uses to describe where things are out in the heavens that we can see from the surface of the Earth. In the equatorial coordinate system, the difference is that the origin is the center of the Earth, and the fundamental plane is the Earth's equator mentally projected out into the cosmos, and that is where they get those primary references. The ecliptic coordinate system, and I have that in yellow because it's important. We're going to talk a lot of ecliptic here in a second. The ecliptic coordinate system is the same sort of a system, but in the fundamental plane is no longer the equator of the Earth projected out. It is now the imaginary plane that all of the orbits of the 9 planets of the solar system are in, and they all are basically in the exact same plane. There are 2 outliers. Mercury is in a slightly elliptical orbit that is a little bit tilted out of the plane of all of the others, and so is Pluto and Charon. So yes, I know Pluto and Charon have been said that they're not they're not a planet. They're dwarf planets, which still has planet in the name, so fuck you. It's still a planet. There's 9 bitches. And the last, fourth, is the galactic coordinate system, which is how we plot where things are out throughout the entire Milky Way galaxy. The origin, believe it or not, is Earth. The primary direction is from a line from Earth back towards the center of the Milky Way galaxy, and the average of all of the stars that we can visibly see in the Milky Way galaxy basically forms a hazy layer that can define that, the average of which is the fundamental plane. And then, believe it or not, they've actually extended this out into a supergalactic coordinate system, which is everything in the known universe that we can observe from where we're at. All of the other galaxies, the average of them form a plane. So that's a little bit bigger than what we're going to focus on tonight. So here's that table that I was saying you. The horizontal system, whoever you are the center origin point. Your fundamental plane is from your eyeball to the horizon. Your poles is the zenith and nadir. That is zenith being straight out the top of your head, and nadir being straight out your feet down to the center of the earth. Okay, so zenith and nadir. And things are described with an altitude and elevation and an azimuth. The zero direction is to the north or the south pole. So as you now, when you hear people using this coordinate system that you've used your entire life, you'll notice that there's missing an elevation, the range, in other words. And the reason is because we just edit that out, because you pretty much are always just talking about, I am standing on the surface of planet Earth and I'm going to another spot on the surface of planet Earth. So we just don't say what the elevation is, because it's just the surface of the Earth. Unless you're flying. If you're flying an aircraft, then we add in altitude. And now you get back to not just a lat long, you get back to a lat long and an altitude. So it is still a three coordinate system. It's just that when you're talking about ground navigation, everybody edits out the altitude or elevation coordinate, because you don't care. You're talking about just walking along or driving along or sailing along the surface of the Earth. The horizontal system is also the only left-handed convention system. That's why when you look at north, 1, 2, 3 degrees off of north are in the clockwise direction, because that is a left-hand circular system, left-hand rule versus right-hand rule. All of the rest, equatorial, ecliptic, galactic, and supergalactic systems, are all right-handed. And you can see there. Now, there's that ecliptic in yellow again, because it's important. And the ecliptic system has two subvariants, if you whether or not you use the Earth as the center of your ecliptic system, or whether you use the Sun, it's barycenter, as the center of your ecliptic system. One is called geocentric if it's Earth, and it's heliocentric if it's the Sun. And it's not the center of the Sun, it's the barycenter of the Sun. So, or the barycenter of the solar system. Barycenter simply means if you take, the Sun is the biggest thing, so its gravity is working on all the 9 planets and everything else in the solar system. But that's a two-way street. Even though they are much smaller in mass, they also have gravity, which is also working on the Sun, which means that if you sum all of the crap in our solar system, and sum where the actual center of that gravitational field is, it's not at the center of the Sun. It's close, but it's actually off center from the center of the Sun. That's called the barycenter. And this is why stars wobble if they have things orbiting them, planets or moons or asteroids or anything orbiting them. Then that actually makes the star wobble, which is one of the ways that celestial telescopy can look out there and go, hey, I can see that star, I can watch it over time, and I'm seeing it wobbling, ergo there are things that are orbiting it. Could be planets, could be asteroids, could be dark matter, could be all kinds of exotic stuff. Sure. Go ahead. Yes. Absolutely. Yes, if you were in a binary or a trinary star system, and then on top of that binary or trinary star system had planets and moons and asteroids and comets and all kinds of things orbiting them, there would be a barycenter that would take all of that mass, all of those various units of mass, and their coordinating gravitational pulls on each other, sum them and find that center. That's the barycenter, which would not be probably in any of those 2 or 3 stars. It would be a mean point somewhere in between them. In actual astronomy, it would be, in actual astronomy, you're talking about observing here from, 100 million light ways away. So they can observe it, and that by definition means it's going to be the sum total of everything working in that system. Yeah, a barycenter is not something man decided. That's something God created, and we can just figure out where it's at. Okay. Anything else? Sure. The answer is both, and which I know sounds like a non-answer, but it depends on which one of these you're talking about. Some of them use plus 0 to 90, negative 0 to 90. Some of them use plus 0 to 90 is up, along the north ecliptic pole, from up out of the plane towards the north ecliptic pole. And instead of using minus to go below the fundamental plane, some of them will use 270 back to 359. You understand? So they use, just like you use 0 to 360 around horizontally, they use 0 to 360 in the vertical plane, but they don't use anything over 90 and below 270. So Star Trek tile, hey, the target is bearing 340 Mark 20 is 20 degrees above. He goes 340 Mark 300, he's 60 degrees below. That make sense? Yep. Okay. There's a lot of stuff here, so I'm going fast. Okay. Now, there are problems with these systems. Okay. And there's just why I think because of the level of simulation that Star Citizen is trying to bring itself to, I think they have been wrestling with these for a while, and I think they've kind of made a decision and gone with, thrown a stake in the ground, made a decision and started building something. And I haven't had this conversation. I haven't heard them talk about it, but based on what I'm seeing in the game, I think, in my opinion, they've made the right decision, because it's the decision I would have made in their place. Okay. So what are the problems with these systems? In the horizontal system, location and time, if you're trying to describe where things are in a solar system like we are in Star Citizen, try to come up with a coordinate system to describe where all of the pieces of the Stanton system are within the Stanton system, then that varies with location and time. If I'm standing on a spot on planet Earth at 10 in the morning, wherever I'm at, I'm going to be looking a different direction out into the night sky or morning sky, if I could see past the blue and see the stars. Then at 10 o'clock at night, I'm going to be 180 degrees around on that rotation of the planet Earth. I'm going to be looking in a totally different direction. So location and time varies on the horizontal system for you to be able, makes you have to now not only go, hey, to be able to see the Big Dipper, I need to look in this direction at this time from this location. Becomes a much more complicated thing. The equatorial system has the problem of nutation. Nutation is, believe it or not, if you watch a top spin and you watch it long enough, you'll notice that the nice perfect spin of the top, as this top starts to slow a little bit, you'll see that the spin starts to wobble a little. The axis that the object is spinning around starts to wobble a little bit. Planets are no different. The direction that the poles, that the axis that our planet is spinning around, those poles, if you projected them out into space, as if you could see them, they do not point in perfectly the same direction at every second. They actually nutate around. There's a little bit of wobble. They vary by a degree or two, plus or minus, back and forth and back and forth. And everything in the universe that spins has this same thing. It has some degree of nutation. Some things that nutation is massive, some of it's really small. Earth's nutation is pretty small. It's only about, I think 1.2 degrees is how much it nutates. But because of that, that means that any equatorial coordinate is now going to be based, it's going to have what's called a time epoch. It's going to depend on what time you measured that. So and if you always come back at the same time, then your measurement is always going to be the same. But if you measure at that same astronomical body 6 hours from now, you're going to be off by, 1/4 of 1.2 degrees. So you're going to be off by 0.3 degrees. It's going to be 0.3 degrees different because of the nutation of the Earth. All right, an ecliptic plane, spherical coordinate system that's an ecliptic, varies with perturbation. And perturbation is a similar effect on the movement of a solar system based on the gravitational pull of everything else that's around it. So our solar system has some amount of perturbation. It as it travels, as the Milky Way galaxy spins, and our solar system out on the Orion arm of the Milky Way galaxy travels around the center of the galaxy over time. Its path is not this perfect circle or ellipse. It wobbles a little bit, not the way nutation does, but it wobbles left and right depending on as it passes other large gravitationally significant objects out there, big, massive. So black holes, other solar systems that we're passing, as we go driving by, they pull on us as much as we pull on them, and that causes wobble as in our orbit around the solar system. That's called perturbation, which means, again, because of that, any measurement you make is going to have a time epoch to it. It means we measured this at this time of day, month, year, etc., and you could measure it a year later from the same spot, and it'll be off by a couple of fractions of degrees. The longer you go from the first time, the more variation there will be. Galactic and supergalactic systems, we don't know what the variation is. We're pretty sure that they're there, but because we cannot get our frame of references, we cannot get a telescope away from the Milky Way galaxy big enough to see the known universe, we cannot measure or even theorize what variations would be out there. We do know through redshift that the galaxies are all floating away from each other at this point. Whether or not that'll be enough to, whether entropy will go to zero, or whether they'll eventually come to a stop and then everything collapses back in. We don't know because we can't observe it and we can't measure it. But we are fairly sure, just because of wisdom, that there probably is variation that we don't even know about. Okay, so what's a CIG to do? What's a CIG to do if we're trying to be as close to a simulation as possible and come up with some sort of coordinate system that works within a solar system? And so my answer, and I believe their answer is the same one, is a custom made ecliptic coordinate system. Model an ecliptic coordinate system similar to the real one, but with a few tweaks, because it's a computer game that makes life a hell of a lot easier on the programmers. So in real life, our heliocentric elliptical coordinate system uses Sol's barycenter, uses our ecliptic plane of our solar system as its fundamental plane. The primary direction is the vernal equinox, and therefore the ecliptic poles are plus or minus 90 degrees out of that, and that will give us our ecliptic lat, long, and range, and it is a right-handed convention system, and this is what the real world uses in seriously solar and near extrasolar astronomy. But Foghorn, that means perturbation is still a problem. And the answer is, yes, it is. Stop perturbating or you're going to go blind. But what about this custom idea of the ecliptic system? And I actually I think it was 2 years ago that I did this presentation on celestial life. I actually did it in 3 parts. But I made this suggestion, and by looking at the star map, what they're doing with the HUD compass system and that sort of thing, I believe this is the same solution that they've come up with. So if you just simply, when you're making your Stanton system or your Nix system or your Pyro system or anything, Terra, if you get, as the programmers, you guys get to put the planets where you want them. So just put them all in an invariable plane. Just make all of their orbits in the same coplanar, and there you have a fundamental plane. What are you going to use that's going to be significant for a primary direction? The answer is pick one. Doesn't matter. Just pick one and say that's 0. What are you going to use as the origin point? Center of the star. And if it's a binary system, put an average center between the two. If you want to vary it closer to the bigger of the two, if they have different masses, then just put a percentage ratio. If this one's 60% and that one's 40%, then put it 60% towards the 60%er and 40% towards the 40%er, and there you go. They can just sort of define that. Okay, so that would be my suggestion. Was, hey, for an origin point, while CIG says that we want Star Citizen not to have any loading screens, that is within a star system. Going between star systems, aka jump points, and their demonstrated colonoscopy simulator of flying through the jump tunnel. That is actually a very cleverly hidden loading screen. Basically, that's flow. I mean, they're calling it object container streaming. Things are gonna, the Stanton system's gonna stream out and the Pyro system's gonna stream in. Okay, in other words, loading screen. Except for we're giving you something to do. You have to navigate a wormhole that looks like probably the inside of my colon when I was young and fit, because it probably don't look like that now. So in other words, you don't need a galactic coordinate system, because in the simulation, those two are not going to exist simultaneously on your computer. Only the one system is going to be in operation. So you really only need an ecliptic. So I would just say the star center is the origin point, the ecliptic plane, because I can make all of my orbits in the same plane. I can just define it that way and go, okay, there's your fundamental plane. Just pick a flipping direction. That way is my primary direction. And now I have the three things that I need to be able to define an ecliptic coordinate system. The poles will be 90 plus 90. And then I would just say, pick a left hand or a right hand as a convention. I would go right hand because pretty much everything else is right handed, with the one exception of a horizontal system. We don't care about that. Okay, so what about perturbation? Well, it's pretty simple. You're the one making the simulation there, CIG. So if you don't model it, it ain't a factor. So just don't do it. Perturbation, just define perturbation, does not exist in this universe. It's modeled as 0, and it now no longer becomes a problem, because you're never actually going to have more than the system you're flying in on any client's computer at once. Whew. Oh boy, here we go. So all of this now, hopefully you now become experts on how CIG is doing their solar navigation and coordinate system. Okay. Now the next one is, how do we orient ourselves on planets without a compass? So the big question is like, you fly up to a new planet you've never been to before. It appears to be rotating, just like every other planet we know. How do we determine its cardinal directions? And the answer is the right-hand rule. Like I said, we're going to hear right-hand rule a whole lot tonight. The right-hand rule is how you determine that. So if you take your right hand and just let your right hand relax normally, so it's in kind of a cupped shape, and imagine that you were going to lay your hand on that planet that is spinning with your 4 fingers pointing in the direction of the spin, then your thumb sticking up out of the top with your right hand is going to be pointing towards the North Pole. That is a human convention. We have defined that. That is how we determine what the North Pole is on any spinning planet. So here within our own solar system, Earth is pretty simple. Our axis is tilted 23 degrees from perpendicular to the ecliptic plane, which means that you put your right hand on planet Earth at the equator, let your 4 fingers naturally cup around in the direction it spins, stick your thumb up, and that red pole up there, that one's defined as the North Pole. Your Uranus is very interesting because its poles are almost in plane with the ecliptic plane. They're at 97 degrees from perpendicular, so they're actually, the North Pole is actually pointed 7 degrees down below the ecliptic plane, which means at one point in its orbit, its North Pole is pointed at the sun, and whatever 25% of its year is around, now it actually has a day-night cycle. Another 25% of its year, when its South Pole is pointed at the sun, it's going to have weird, one hemisphere is all day, one hemisphere is all night, and then 25% is going to be back to having a sort of a normal day-night cycle. Seasons on that would be just heinous. Venus is the other odd duck in that its axis is almost 180 degrees out from everybody else. Venus is basically upside down. So if 177 degrees, it's 3 degrees away from being perfectly upside down, inverted to everybody else. So some people have said, I've heard people say, Venus is spinning the wrong way. And the answer is no, it's not. Its poles are inverted. Its North Pole is actually sort of down when compared to the other 8 planets in the solar system. And you can see those little diagrams of the right hand, how that would look to defend that. So you can go to any planet, and if you can watch it from orbit and watch it spin, you know where the North Pole is. Okay? Through the right hand rule. And if you have the North Pole, then you have the South Pole. If you have the North Pole and the South Pole, then into the spin is east, out opposite the spin is west. In other words, on all of these planets and moons in the Stanton system, some people may have wondered how Foghorn always seems to know where east is. Of course, it's where the sun comes up. That's not, oh, that doesn't work on all planets. The answer is, well, if it spins, it does. Because it's a convention. It's a convention of north being right hand rule. That's that pole is the North Pole. Okay, so what's the more practical? I've done a lot of theory here so that people understand how we get to these stuff, and then that Star Citizens actually is, for better or worse, attempting to be the best damn space simulator that it can be. Well, it could be better. But that's at least their marketing slogan, and they're actually giving it a go. Now, more practically, how does that mean that we can find our way around on these planets? And that one of the things that they've given us so far is the orbital markers. So there's always 6 around every planetary body, whether it's a planet or a moon. If they have orbital markers, which are just navigational points in your system, where it knows where these things are at. There are all the orbital markers are 90 degrees out from each other, all 6 of them, because it's 3-dimensional sphere. The good news is that OM1 and OM2 are always in the same spot because they are, by definition, OM1 is the North Pole of the planet. It always sits over the North Pole of the planet, and OM2 is always over the South Pole. 3, 4, 5, and 6 are nice and easy, but they move because they are distributed at 90-degree intervals around the equator geostationary orbit. And just out of convention, they've made 3 and 4 on opposite sides, 5 and 6 are on opposite sides from each other. So you can fly up to any planet or moon like Lyria here and spool your drive with nothing set in your star map, no route set in your star map. If you just spool your drive and look outside when you're close enough to the planet to get its local markers, and you'll also get a whole bunch of other markers for anything that's down on the planet and everything that's within visual range for it to be able. But you will also get these 6 orbital markers, and they will be laid out something like this. So OM1 is the big one to remember because it's always over the North Pole, and 2 is always over the South Pole. All right, OM1 is north. Yes. Depends on the... it is a set distance from the surface for that planetary body, because the size of the planetary body comes into it. So Damar's, like if you go to OM, any of the 6 OMs on over top of Damar, and then you look down and find a ground target that you can measure with your nav system, an aid station or something down there, you're going to be like, okay, I'm only like 180 kilometers up. You go to, and that's because Damar is very small. You go to Microtech, which is, I think it's the biggest planet, not counting Crusader, because they haven't finished Crusader and Orison. But you go to Microtech, and that thing's like 8,000 kilometers in diameter. So you go to one of the OMs, look down, and it's not 200, it's 1,200. So the 6 at a place are all the same distance above, because they're geostationary for that planetary body. But they are not a standard height above the ground between different planetary bodies. Does that make sense? I would assume... Yeah, 25% of the radius or something like that. Yes, I'm sure there is. I don't know what it is. That would be something, that would be something that would be in their code. So I'm sure somebody could crack that. Or you could ask them. Can we go back to slide 27? There you go, Mark. Does that make sense? We could. I don't want to. I understand as long as you understand the principle that, oh, okay, this is how I can use this. And now I understand how they got here to this. Now I can understand that, okay, OM1 is always north. I don't just have to take somebody's word for it. I understand the science on how they got there and why is OM1 always north and why it's that important. Why does the sun always rise in the east no matter what spinning object you are on? Okay, so yeah, sun rises east, sun sets west. That's the same on any of the planets in the Stanton system, and I imagine through all of Star Citizen. Could always change. They could do something different if they choose to. And oh, by the way, we do have a HUD compass coming in Alpha 3.12, we believe. We know it's coming. It may not be coming on 3.12, but I think so. All right. So that's good news. Last thing we're going to finish up here is just traffic patterns and coming into land at places, and we were talking about earlier. There are more than the two that I'm basically going to show you. But I don't think they have a place in Star Citizen. I could be wrong. But we'll see what develops in the future. They're pretty simple. What the 99.9% of departures and approaches that you're going to do in Star Citizen are going to be what's called diverse departures, which simply means we're going to use the see and avoid concept. I'm going to take off or I'm going to approach the airbase where I'm going to land. And I'm going to look outside the window, and I'm going to use my radar and my sensors, and I'm going to see all of the other traffic, and I'm not going to hit them. That's what the see and avoid concept simply means. So it means you don't have to actually fly any sort of a pattern. Just fly from, fly from where you took off on the pad or the hangar, came out the doors, turn, once you get airborne, get gear sucked up, get out of a landing tunnel thingy or takeoff tunnel thingy if you're at Lorville or Area 18. Once you get clear of that, off you go. Just turn in the direction towards your destination and get this train rolling. Clear your own flight path on the way, and just like I said, just direct routing. Just get there. Direct routing to your destination or to your landing pad if it's a diverse approach. Can start from anywhere. So that's the easiest one for them to model and to do, and that's basically what Star Citizen is, how it works. However, diverse departures and approaches have an Achilles heel. And particularly now that they've added weather, the problem is that to do a diverse departure, you have to be able to do see and avoid. You have to be able to, so it assumes visual meteorological conditions, what we call VMC in the flying world. If you don't have VMC, you really can't do a diverse departure or approach. You're going to have some sort of an instrument departure or an instrument approach. Which is why I'm also going to talk to you a little about straight ins and how this is Foghorn designing a straight in for the Star Citizen universe. Okay, so these numbers are based on Star Citizen. These are not based on real world. I mean, it's templated from the real world. The real world, ILS type of straight in approach is used as inspiration and as template, but everything tweaked for Star Citizen. So. We'll just say standard final approach fix on a straight in is 1 kilometer from the threshold of your intended either pad, hangar, runway, whatever it is you're going to land on. And at that point, the final approach fix, you need to be slowed down to 100 meters per second or SCM, whichever is lower. Aligned with the threshold in a straight line. At that point, you start your descent towards the landing threshold. Make sure your gear is down, and that's where you'd make a comm call, such as Wolf 1, final approach fix gear down, full stop. That is made to tower so that they know to look out there in the direction of wherever they just cleared you to land at and are looking to go there. As you are descending towards it, you're also going to be slowing down. You want to be probably short final with something 35 meters per second or as required. So less, make sure you're aligned for landing. This, at some point, if they ever start putting in some sort of an instrument approach system, it will be based on this, because this is how instrument approaches are done. In real world, it's also the simplest way because it's just straight on. You're not streaming the Discord questions, so Twitch doesn't have the questions, only the answers. How is that? He says. Wow. Okay. I wonder how that got messed up. Hey, TD Trader, unmute for a second. Say something to me, just so I can see if... Nope. Okay, we'll press on. All right, we're done. Almost. Actually... Huh. Very strange. Yep, for some reason my desktop audio does not seem to be getting streamed out, which is very, very, very odd, because it's... all of the switches say it should be. Okay. Technical problem on my place. Oh, there it is. Now it starts working all of a sudden.
Okay.
Okay, thanks. All right, so in practice, how would this look, say, coming into Port Olisar? This is how it would look laid out. So out about 1 kilometer, you're just gonna be measuring that from Port Olisar's PIP. So yeah, is it perfectly actually a kilometer from your landing threshold? No, it's going to be off by a little bit because the station's PIP is going to be, over here somewhere, but it'll be close enough for you to be able to fly this pattern here in space VMC. Space is pretty much all VMC unless they're going to do some sort of gas cloud tech that is so thick that it actually is as bad as planetary clouds with obscuration. But if they ever put in an instrument landing system, I guarantee it will, because it can't get any simpler than this. This is the pattern that they will. The final approach fix may not be 1 kilometer. They may decide to put it out at 2 kilometers or something like that. I doubt they would go that far, just because it's just, if you're doing 100 meters per second at 1 kilometer, you're 10 seconds from touchdown, and you're going to be slowing that entire time. But anyway, so that's it in a nutshell. Is there any other questions before we get out there and fly? I've been talking for an hour. I'll tap dance for a few seconds. Alrighty. No other questions. I'm glancing up. Glancing up at the Twitch chat. See if there's anything else that I missed. I don't think so. I think we got all the questions. So.
And next week we're doing Keplerian orbital elements, right?
We're doing what next week?
I think he was joking.
Oh, joking. Keplerian orbital elements.
Actually, I have a question about the hoped for compass. Is that just going to be a planetary compass for when you're down on planets, or is it going to be for out in space too?
Oh, sorry. No, it'll be both. Which means that at some point, I suspect the same time that your pitch ladders kick in or off, even yes, I know half the time they don't kick off. But when you go down onto the planet, the system will turn into a horizontal system that you just learned about, right?
Yeah.
And then when you get into space, it will kick into some, I don't know, it might stay as a horizontal system just up in space referencing the ecliptic plane, or they might go to a full ecliptic system, which is what I would expect because it's higher, it's more fidelity, and it's not really any harder to do. So a lot of information, very fast. That's why we record these things and upload them to our archive. So
a quick note on that compass too. That's only going to be for Aegis ships because they're the ones getting the first redesigned HUD. And like you said, we don't know if that's going to be a 312 or not. So the other ships will come along, but it'll probably be in later patches.
Yes. Absolutely. 100% true. I do remember hearing all of that and totally forgot it. So
I have another question. You may not have said anything about this, but with all the talk of data running and stuff like that, they sure make it seem like knowing the coordinates of something requires some kind of giant computer system rather than just 4 numbers.
Yeah, exactly.
Do you know anything about where they're going to go with that?
No. Short answer, not really. I mean, yeah. The compass is super important because a lot of, particularly if you're talking about knowing where secret things are, if you're,
You got to have a way to get yourself
you
there.
got to have a way to get yourself there, and if it's a secret thing, you're not going to put a nav point on it, which means that the only way to get there is through dead reckoning, which means that you have to have a start point, some nav point, and then you have to have head 280 for 10 minutes at 100 meters per second, turn right to 340 and travel at 200 meters per second for 10 minutes, that kind of thing. That's dead reckoning. To get you to that secret place like Jumptown or the drug lab or the orphanage or any of those kind of things, versus now, whereas really the only way you can find them is through what's called pilotage, which is, if you've ever been there before, if you were new to Star Citizen and didn't have anybody ever show you where those things are at, you would have to go through the personal tab on your contract manager and do the criminal missions to the point that they would send you there. Then you would get a PIP, a nav point for just that mission to get you there. And then before you leave, take off and fly around it for a little while and learn the geography so that you could spot it from space. I haven't been to Jumptown in probably 6 patches, but back in the day, pretty much everybody who had ever been to Jumptown knew how to, fly to Yella, fly to I don't remember which OM it was. I think 3. Go to OM 3, and then knew how to look down and see the topography from the orbit and go, okay, you find the mountain range that looks like a duck, and then you go from that, you look northwest of that, and then you find the biggest of the 3 craters, blah 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 blah. And that's just called pilotage. Pilotage is, I look out the window and I recognize that tree, I recognize that rock, I recognize that mountain, therefore I need to fly this way. Versus dead reckoning, which is all done by math.
I had a question about the instrument approach in space. While clouds could be an issue, one thing that's already an issue is flying into the sun.
Yeah.
It's basically impossible to see anything, and you could just be flying straight into an asteroid at any time.
Yeah, I think at some point they're going to have reactive glass that'll darken around the sun, because they know it's a problem.
Yeah.
And they've said that they know it's a problem. And again, when they're just trying to get servers to mesh and eyes to cache, that's stuff that's farther down the road. It's not that it's not important. It's just there's a priority to the tech. So.
Have you also heard anything about downward-facing cameras or landing radar or something like that?
John Crew and company, who do vehicle feature stuff, there used to be, when you put your gear down, or I think when your gear was down and you were within a certain range of a landing pad, your 3D holographic radar changed modes, and instead of you seeing the 3D holographic radar with the little triangles and the lines, it turned into a 3D hologram of your ship and the pad, and it had scrolling blinking arrows kind of showing you directions to slide left, right, up, down, forward, back to get you over it. So you had this 3D thing where you didn't need a downward facing camera, because you could just look down there and fly your little holographic ship down onto the pad, and it worked really well. And that was the way it was all the way back in 2.6.3 when I started playing, which was 2017. And that worked awesome. And then in 3.0 it went away and hasn't been back since, and everybody's been bitching because we want it back. They know I can't remember if it was John Grew or what's his name, the Bug Smashers guy. I think one of them said, yeah, we want that back too. We still have it. We're gonna bring it back in at some point. So I suspect that they're gonna do that versus the downward facing camera. You can kind of create your downward facing camera now just by going F4 into third person view.
Sure, that's what everybody does. But
you can save camera positions.
Right.
Yeah, so that's you know, whenever I get in a new ship that I don't have camera positions already set for, one of the first ones I do is I go get the top down view and zoomed out enough that I can see sort of around the spacecraft, you know. And then I save that as like hold F4 down and long hold number pad 8. So that's my top down view button whenever I'm, you know, trying to put the Carrack into a vertically landed hangar, because they all seem to be freaking anorexic.
Is this for pads and hangars only, or would it also work in just landing on the ground somewhere?
Anything that was a pad. So,
Okay, so
if
but
you're just
no-
out on dry ground, it didn't kick in for that. Well, 2.6.3 we couldn't go down to planets and moons anyway.
Oh, okay.
So it was only on pads. But
There's an additional problem there, which is if there's rocks around and stuff, it's really hard to see. Am I landing on some big rock outcropping that's gonna, you know, do
Yep.
something bad? Yeah.
yeah,
all right.
my favorite ship is the fly is the Carrack. And so yeah, every time I try to land somewhere, it's always a 10-minute operation in the last 5 feet above the ground of like, oh, am I going to land on? No, I'm going to have one gear up on that rock. No, if the tree's in the way, you know. So I feel you. All right. Anything else? We're going to sign off and go fly.
Actually, I have one other question.
Okay.
I have been seeing a lot of trouble with the auto landing, either with getting hung up on pipes and other stuff near the pad, or getting into this wild swinging thing that the autopilot does, where it overcorrects and then overcorrects the other way. And
Really?
eventually it dampens it out, but it takes a long time. Has anybody else seen that?
I have not, but
Okay.
I see people typing.
It's 100% of the time with my freelancer.
Yeah.
So
Well,
it's not even.
don't use auto
sometimes-
land.
Well, I just don't do it, but you know,
Yeah.
it's obviously a bug. I was
Right.
just not sure if it was a bug for everybody or just a bug for me.
I kind of never use Autoland, so I wouldn't know. TD Trader asked, how do we set safe camera positions? Okay, F4 obviously takes you into third-person mode. So if you're sitting in an aircraft seat, that takes you to third-person mode of the spacecraft. So you're going to be high and behind is where I think it defaults to. Your number pad buttons 1 through 9 are save and load buttons for camera positions. So you can, once you get out in third person mode, you can use your mouse to orbit your camera around. If you hold F4 down and hit the plus or minus key, you can change the field of view. So you'll go plus, hold down F4 and go plus a bunch of times to get your field of view as wide as you can. Holding down F4 and using the arrow keys and page up, page down will move the center point of the camera around relative to the spacecraft. So in obvious ways. So forward, up arrow, down arrow moves forward, back, left, right key arrows move left, right, page up, page down moves vertically up and down from where you're at. And then once you get to a position that you're like, yes, I like that camera spot right there, hold F4. And if you long hold any key 1 through 9 on the number pad for longer than 1 second, then it saves. And then now you can move the camera to anywhere you want. And if you hold F4 and short press that previous saved position, that's previous. So if you saved it in button number pad 1, then if you short press number pad 1, it'll move the camera automatically to that spot. The any key 1 to 9. That from our master of IT there, Exnor. Okay. Any last questions? A lot of information, so everybody's brains are probably smoked. That wraps up this installment of Academics with Foghorn. Hope you found it interesting and helpful. If you have any questions I didn't answer, please feel free to contact me via email, Discord, Spectrum, or of course the comment section below if you're watching it later on YouTube and or Twitch. I will answer it to the best of my ability as soon as I see it. Member or visitors alike, please hit those follows and subscribe buttons as appropriate. Leave us a comment. We actually read all the feedback, and it really does help us as we're always striving to improve our content for our members. You can find out more information at aurorarepublic.space, our bespoke website. And, of course, on Spectrum, if you're a nerd, at robertspaceindustries.com/org/Aurora Rep. See you next time. Foghorn signing off and wishing you a very pleasant remainder of your morning, afternoon, and or evening. And thank you very much for watching.